the previous lecture, I derived the force on a current distribution to be the gradient of m dot b, and we also through this identified that the energy of a point dipole in a magnetic field is going to be minus m dot b, where m for the current distribution is defined as 1/2 integration dV r cross j r. In this lecture, I want to derive the torque on a current distribution in a magnetic field and show, just like an electric dipole, the torque is going to be equal to m cross b, with m again being given as integration dV r cross j with a factor of half in front. So, let us do that. Again we learned how to do these things, and we should know when we do electromagnetic theory that current gives the magnetic field, the current loop gives a magnetic dipole moment, and we should be able to derive all the torques and forces from that. So, again let me motivate first physically, just like we did for the force, how this torque arises. So, for this again I will consider this loop carrying current I in the phi direction. Its axis is along the z axis, and it is in a field B. For simplicity, I now have B, which has a z component and x component. So, that B is B x I plus B z k, and the uniform, the components are uniform. You will see that in this case, in the first approximation, I do not really have to worry about the variation of B as I had to do in the force, because that was the first non-zero force component came from gradient of B. Here I do not really have to do that. So, what I have is this coil, and if it is in this uniform B z, then the force on the sides is going to be all I cross or phi cross z. So, force due to B z is going to be phi cross z in this direction, which is in the direction of s unit vector. So, the force due to the z component is all radially out and all uniform, and therefore, this force vanishes and gives 0 torque also, because r cross dF is 0. So, the only force comes from this dx Bx component. This is I, and there is this uniform field B in the x direction. Let me consider a small element of current like we did in the force calculation here, and this is dl. Then the force dF is equal to I dl cross B in the x direction. So, this is going to be equal to I dl is r d phi in the phi direction times B x unit vector is x unit vector, and there is a cross product. Now, I know that phi is equal to minus sin phi x plus cosine phi y, and therefore, this small force dF is I r d phi Bx cosine phi in the z direction with the minus sign in front. So, this is a force I r d phi Bx cosine phi z. So, what do we have? If I have this loop carrying current I in the phi direction, and this is in this field Bx x, then the force on a small element out here is dF equals minus I r d phi Bx cosine phi, and is in the z direction. The torque on this, d tau, small torque on this element is going to be r cross dF, and r is in s direction. So, this is going to be r s cross z with a minus sign in front, and I have I r Bx cosine phi d phi. Now, S is equal to cosine phi x plus sin phi y, and therefore, d tau is minus I r square Bx cosine phi is outside, and then I have x cross z, which is minus y cosine phi, and then I have y cross z, which is plus x sin phi, and outside there is cosine phi d phi. And tau therefore is equal to x component with a minus sign integration I r square B x sin phi cosine phi d phi plus y component I r square B x integration cosine square phi d phi 0 to 2 pi. The first term vanishes, sin phi cosine phi integrated 0 to 2 pi is 0, and therefore, I get the torque to be equal to y I r square B x and cosine square phi d phi 0 to pi is pi. So, this comes out to be pi r square I B x in the y direction, and this can be written as, if total B was B x, this can be written as torque equals m cross B, because m is pi r square I in the z direction cross B is in the x direction. So, we found by the simple argument that tau is m cross B. Let us now do this in a rigorous mathematical manner. For that, I again consider this current distribution around the origin, and the torque on this current distribution is going to be the force on a small element cross R integrated over volume. So, actually this is not the correct way of writing it. I should actually write, if I take a small element, let me make it carefully. Here is a small element of current, red one, then it should be integration R cross df, which is nothing but integration R cross df is calculated as j cross b dv integrated over. So, this part is df. This we had seen earlier. So, my torque on this current distribution is integration, I will bring dv in front, so that I can manipulate the rest of the terms easily, R cross j cross b. So, let us calculate the alpha component of torque, which is going to be dv R cross j cross b alpha term, which is equal to integration dv epsilon alpha beta gamma r beta j cross b gamma, and this b is b at the origin, because I am not taking any other r dependence, no r dependence. Why am I doing that? Any added r dependence will give higher order multiples. How do I see that? Let me write b equals b at 0 plus r dot grad acting on b. Then the torque comes out to be integration dv epsilon alpha beta gamma r beta j cross b 0 gamma plus dv epsilon alpha beta gamma r beta j cross r dot del b 0 gamma. This, as you see, 2 r's, r square, and I want to neglect that in comparison to the only the r term. It is a very small distribution. So, this first term gives me dipole, and this is giving me higher order multiple. So, I am not taking that into account, because I am interested right now only in the dipole term. So, let us write this again. So, I am considering this current distribution in a magnetic field B, and have written the alpha component as integration dV epsilon alpha beta gamma r beta j cross B at 0, which is a constant now gamma, which I can further write as integration dV epsilon alpha beta gamma epsilon gamma L m r beta j L B m. Which can be written as integration dV alpha or epsilon gamma alpha beta. I have done 2 permutations, beta gamma and then gamma alpha. So, sign does not change, epsilon gamma L m r beta j L B m. And using the identity for the products of two Levi-Civita symbols, I write this as integration dV delta alpha L delta beta m minus delta alpha m delta beta L times r beta j L B m, which is equal to integration dV. The first term will give me r beta j alpha b beta. Plus the second term will give me integration dV R L j L B alpha. Recall that dV R L j L is 0. This you can also see from this expression when I write integration dV R beta j alpha is equal to minus integration dV R alpha j beta. If alpha equals beta, the term is 0. Even if you sum it up, it is all 0. So, I get tau alpha is equal to integration dV R beta j alpha b beta, which I can write now as tau alpha is equal to integration dV R beta j alpha b beta as equal to integration dV 1/2 R beta j alpha minus R alpha j beta b beta, which is 1/2 integration dV epsilon beta alpha gamma R cross j gamma component b beta. This, by switching beta and alpha twice, I can write as integration dV epsilon alpha gamma beta R cross j gamma b beta, and this is at the origin, which is nothing but epsilon alpha gamma beta 1/2 integration dV R cross j gamma component b beta component 0, which is nothing but m cross b alpha component, where m equals 1/2 integration R cross j dV. And therefore, the torque on this current distribution comes out to be m cross b. So, this shows that to the lowest order, the torque is m cross b, where m is the dipole moment for the current distribution. Using this, we can again find the potential energy of m in a field B. Let us do that then. So, to find the potential energy, I will do some work on this point dipole. I am making it big. Here is this point dipole in some magnetic field B, and I am going to rotate it. Let me rotate this point dipole by angle d theta vector. Then the work done by us, and for potential energy it is always by us, is going to be minus m cross b, because that is the torque I have to apply, dotted with d theta. This is d w, which by cyclic rule I can write as minus d theta cross m dot b. What is d theta cross m? So, this is m rotated by angle d theta. This is delta m, the change due to this rotation by d theta. So, this is nothing but delta m dot b with a minus sign, or d m dot b, and this immediately gives you that work done will be minus m dot b. So, we find that the potential energy therefore is going to be minus m dot b. This is the same as obtained by the force formula earlier. So, now let me conclude this lecture by saying that we have derived torque on a current distribution kept in a magnetic field, and shown that torque is m cross b to the lowest order, where m is 1/2 integration d v r cross j r. And third, using this, shown that potential energy u is equal to minus m dot b, same as obtained through the force. Thank you.